welcome to the course on advanced machining process. Today we shall discuss about abrasive water jet machining process. So this is one type of advanced machining process, mechanical type of advanced machining process. So already we have discussed abrasive jet machining, and here today we are going to discuss abrasive water jet machining process. So before starting off that process, we shall discuss use of abrasives in different mechanical type machining process. So this is the outline of my presentation. So first we shall discuss about abrasive water jet machining, and then we shall discuss about the working principle of abrasive water jet machining process and different elements of abrasive water jet machining process, and then parametric study, how these finishing parameters and machining parameters are affected on abrasive water jet machining process. And we shall discuss after that visualization of abrasive water jet machining under camera. And then we shall discuss about the applications and process performance of abrasive water jet machining, and finally we shall conclude about this process. So first introduction. So here we are going to discuss about different applications of abrasives in machining process. Okay. So already we have discussed these abrasives. It can be used in conventional machining process, conventional finishing processes, and also machining process, like in grinding, honing, and lapping operation. So these three are actually conventional type finishing processes. Okay. So grinding, honing, and lapping. So in grinding, actually abrasive particles are bonded together, and in honing and lapping operation, these abrasive particles, loose abrasive particles are used. Honing also people use honing stick. Their abrasive particles are bonded together. Okay. So other than this process, there are other super finishing processes also where abrasive particles are used. So after that, these abrasive particles are used in abrasive jet machining. Already we have discussed. Here carrier medium is the air, or any inactive gas also we can use. So generally air is used because it is cheap and it is cheap and easily available, so air is mostly used. And in abrasive jet machining, this disadvantage is that here material removal rate is low, and surface finish and machining efficiency is low in case of abrasive jet machining process. So already we have discussed in abrasive machining, jet machining, there is a divergence of the flow. So when this abrasive jet comes from the nozzle, so and it comes to the atmosphere, okay, so at that time, because of the friction with the air, so there is a divergence of this jet. So because of this divergence, this curve generated in case of abrasive jet machining is high. Okay, so we get lower efficiency and lower accuracy of this process. So there are different improvements in jet cutting technology. So we shall discuss in abrasive water jet machining. So there are different improvements are there. So after that, these abrasives, loose abrasives, are used in ultrasonic machining process. So there we have used slurry as the carrier medium, where base medium was deionized water, or water also we can use, and abrasive particles are mixed in that water. And this tool actually vibrates with a high ultrasonic frequency, and because of this impact of these abrasive particles on the workpiece surface with a high velocity, okay, so these small craters are generated. So here slurry is the liquid and tool vibrate with ultrasonic frequency. In ultrasonic machining also we can see that material removal rate is very high because machining is done by small abrasive particles. So here also in ultrasonic machining process, efficiency is very less. In another process where we use abrasive, loose abrasive, that is called abrasive flow finishing process. In abrasive flow finishing process, this viscoelastic base medium is used. So it acts as a self-deformable stone, and here there is no ultrasonic vibration of this tool like in ultrasonic machining process. So use of pneumatic or hydraulic force to reciprocate the media from top media cylinder to the bottom media cylinder. Okay, so while flowing this media through this cylinder, and you have to move the fluid through the finishing zone, and like that polishing is done in abrasive flow finishing process. So in abrasive water jet machining process also loose abrasive particles are used. So there are different advantages of abrasive water jet machining process. So there is no dust because this abrasive water jet machining, it is done in water environment. So water mixed with abrasive particles comes from the nozzle for machining. Okay, so that's why, because of this, water is the base media is used here. So there is no dust. What in abrasive jet machining process? So we have seen that these dust particles are generated because these abrasive particles get crushed, and when it is mixed with the air, so these dust particles actually come outside. So that's why you have to have a dust collection system in case of abrasive jet machining. But in abrasive water jet machining process, there is no dust because machining environment is done in water. Okay, so there is no dust, no, and high cutting speed because here media base media is used as a water. Okay, so abrasive particles here comes with a very high velocity, around 900 meter per second. So that's why high cutting speed is there in case of abrasive water jet machining, unlike abrasive jet machining process. So no thermal stresses because abrasive particles are hit by abrasive particles hits the workpiece surface. Okay, so that is heat generation is very less. So tool, like in conventional machining process, here tool does not touch the workpiece surface. Okay, so heat generation is less. Also, whatever heat is generated, it is taken away by the abrasive water jet. Okay, so it is taken away by the abrasive water jet, whatever heat is generated. No delamination, like in composite material. While cutting this composite material, there is a delamination phenomena occurs. Okay, so one layer actually means while cutting, these layers actually separates out, so that is called delamination of composite material. But in case of water jet, abrasive water jet machining process, this kind of phenomena of delamination does not observe. So no fire hazards because temperature generation is very less, so that's why there is no fire hazards in case of abrasive water jet machining. Low level of power requirement, so this is another advantage of abrasive water jet machining, and high edge quality also observed in case of abrasive water jet machining process. Okay, so now what is the working principle of abrasive water jet machining? So here we can see that this abrasive particles, it is coming with an angle and it is attacking. So here abrasive particles are coming, these abrasive particles are coming with an angle. Okay, so it is hitting to the workpiece surface. So there are two forces we can see here. This Fy, this force, actually this force is actually responsible for penetrating these abrasive particles into the workpiece surface. So it helps in penetrating the abrasive particles into the workpiece surface. Okay, so there is another force, this Ry, this R force is the resistance force by the workpiece. Okay, so this Fy is balanced by this resistance force. Okay, so this Fy is helps in penetrating this abrasive particle into the workpiece surface, which is resisted by the reaction force Ry, and there is another force, this force Fx. Okay, so this force Fx actually it helps in cutting the surface on cutting from the workpiece surface. Okay, so this Fx actually helps in cutting operation, and Fy it helps in penetrating into the workpiece surface. So here Fy is responsible for penetration and Fx is responsible for removal of material in the form of chip due to the shearing action from the workpiece surface. So this figure actually it is taken from published by Hassis Muhammad, a modeling study of metal cutting with abrasive water jets, Journal of Engineering Materials and Technology, Transaction of ASME, January 1984, volume 106, page number 88 to 100. So another figure is there. Here we can see that this abrasive jets, it is coming from this nozzle. Okay, so there is a traverse velocity of u, means this jet is moving with a velocity u with respect to the workpiece surface, and this abrasive water jet, it is coming with a velocity u0 at the workpiece surface here. It is coming with a velocity u0 at the workpiece surface. Initially this diameter of this jet was d1. So while impacting into the workpiece surface, you can see that this diameter actually it is increasing. Okay, so this diameter of this abrasive jet, abrasive water jet, it is shown into the workpiece surface, inside the workpiece surface. Initially it impacting with a diameter of d1. So after impacting, actually it will do this these particles, actually there is a means tilting of these particles. Okay, so these particles, it is tilting here, you can see. So here this diameter is more than whatever it is diameter it is coming inside the on the top surface of the workpiece. Okay, so this each abrasive particle, if we consider, it has two velocity component. One is velocity vh, which is perpendicular to the workpiece surface, which helps in penetrating into the workpiece surface, and this vx, it helps, this vx actually it helps in cutting the workpieces, cutting on the top surface of the workpiece. Okay, so this figure also taken from ASIS, from transaction of ASME. So another figure we can see here. So this is the entry to the workpiece surface, and this is the exit from the workpiece surface. Here also you can see this this abrasive jet, it is perpendicularly, it is hitting on the workpiece surface, but there is a trajectory motion. Okay, so this velocity, actually this direction of this abrasive water jet is actually changes after it hitting to the workpiece surface. You can see just this is the depth machine surface just below the workpiece. We can see this kind of striations actually generated on the workpiece surface, which is unwanted. Means whatever workpiece surface is generated on the workpiece surface, if you are not making, if you are making through holes by this abrasive water jet, then it is okay. But if you are making a blind surface, blind machine surface on the workpiece, so you can see this kind of striations are generated on the workpiece surface. Okay, so at the end also you can see this kind of this workpiece surface, here also this kind of striation generated. Okay, so at the exit. So you can see that this cross sectional, so this figure is the cross sectional view of the machine surface. Means after machining we have taken a cross section, and on that cross section we have seen this kind of striation marks on the workpiece surface. Means whatever the particle trajectory is there, so individual abrasive particle trajectory you can see on the workpiece, on the cross section of this workpiece you can see this trajectory. So initially actually this erosion, this machining is due to the erosive action by these abrasive particles. After that there is a local machining chamber generated. So on that local machining chamber, it is a mixing chamber, it acts as a mixing chamber of abrasives and water jet. Okay, so abrasive water jet, there is a local mixing chamber. So at the local mixing chamber, what happens, this this machining is due to the deformation. So initially at the workpiece surface, this machining is due to the erosive action of this abrasive water jet, and after that this machining action is due to the this deformation at the bottom surface of this machining zone. So here also you can see this kind of striations are generated, which is unwanted. So this figure also it is taken from Muhammad Hasis and from transaction of SME 1984, where they have shown that they have modeled actually this abrasive water jet. They have modeled there in their paper. Okay, so what is the working principle here? So here in abrasive water jet machining process, these abrasives along with abrasives, actually it is coming from the side of the nozzle, and at the center of the nozzle actually water jet, it is coming with a very high velocity. So maybe around 400 megapascal pressure is generated from an pump. Okay, so from an intensifier, 415 megapascal pressure is generated, and because of this highly pressurized water, when it is coming through this nozzle, it gains high velocity. So this velocity is around 900 meter per second, and at this high velocity, when this water jet is coming through this nozzle, at the side of the nozzle actually these abrasives are fed. So these abrasives are actually sucked by this abrasive water jet, or by this high velocity water jet, and inside this nozzle there is a mixing chamber is there. This abrasive and water jet actually mix there. So after mixing this abrasive water jet, it is coming through the nozzle. Okay, so while coming through this nozzle, their velocity is around 800 to 900 meter per second. So when this abrasive water jet, high velocity abrasive water jet, when it is impinging or impacting on the workpiece surface with a very high velocity, because of their high kinetic energy, this kinetic energy, so it hit on the workpiece surface, and when this high velocity abrasive water jet hit on the workpiece surface, it removes the material because of erosion from the workpiece surface. Okay, so this kinetic energy is used, high velocity kinetic energy of the high velocity jet is used for the machining purpose. Okay, so mixing of water jet and stream of abrasive takes place in the mixing tube. So rapid rise in the abrasive velocity occur in the mixing tube in the nozzle, and when this impingement of an abrasive on the work material takes place, momentum transfer of half mv curve occurs. Okay, so this leads to the removal of material by erosion, shear, brittle fracture on the workpiece surface. So pressure, this water jet pressure is maintained at 400 megapascal, and jet velocity is maximum jet velocity is 900 meter per second. So there are two modes of machining what I discussed in earlier figure. So cutting in the upper part of the curve is due to the erosive action, and cutting to the lower part of this curve due to the deformation action. Okay, so because of this, two different models are there, two different mechanisms are there. This abrasive water jet actually, this jet velocity of this jet actually diverges in the deformation zone. Okay, so this is the setup or abrasive water jet machine. Okay, so these are the links actually where you will get more information about this abrasive water jet machine. Okay, so this is the control panel here. You can write your program, and this is the water tank here. This is the water tank, and this is the XY table is there. You can move your table, and you can make any kind of complex shape on the workpiece surface. And this is the nozzle here. Okay, so and there is a this abrasive container is here. Okay, so you can see all this thing clearly in the next figure. Okay, so you can see the same abrasive water jet machine here. So this is the water reservoir here. So this is the nozzle. You can see this nozzle in excited view here. So this abrasive water jet is coming through this nozzle here. So you can see when this abrasive water jet is coming, and it is traversing with a velocity u. Okay, so with the traverse velocity u, you can see the cut marks on the workpiece surface. So these are the cut marks on the workpiece surface. So this is the abrasive water jet here. Okay, now here this is the abrasive tank. So from here actually these abrasives are mixed, are coming, and it is mixed into the mixing chamber. So this is the CNC control panel here. So here from here actually you can write your program, and you can move your this workpiece. Okay, so to cut any complex shape of the workpiece. So this is the another view of this abrasive water jet machine. So this is the abrasive chamber here, and this is the nozzle here. You can clearly see this nozzle, and this is the workpiece here. Okay, this workpiece is kept over this table. It is properly fixed here, these abrasives. Okay, so this is the chamber, water chamber is here, and this abrasives through this pipe actually it is mixing to this mixing chamber, and then this abrasive water jet is coming through this nozzle, and it will come with a very high velocity. Okay, so it will remove it will do the machining action on the workpiece surface here. Okay, this is the another view of this abrasive water jet machine. Here you can see this chamber here, water chamber here. Okay, so this abrasive water jet machine basically it is used for cutting purpose. So that's why it is called abrasive water jet cutting or abrasive water jet machining. Okay, so people also call it abrasive water jet cutting process also. So any kind of material, either electrically conducting or electrically non-conducting material, hard or brittle material or soft material, any kind of material can be cut or machined by this abrasive water jet machining process. So like non-metals, the ceramics, composites, rocks can be machined by this abrasive water jet machining. Okay, so like metals, copper, aluminum, tungsten carbide, lead, etc. can be cut by abrasive water jet machining. So one thing we can remember here. Okay, so here there is no fire hazard. Okay, so it can be used, this abrasive water jet machining process can be used for making holes, making drills in mines, in coal mines. So because this water jet is coming, so this water with the jet actually it will inhibit with the formation of heat. Okay, so whatever heat is generated, it is taken away. So there is no fire hazard in case of abrasive water jet machining process. So what are the operations can be done? So these are the operations like drilling operation, cutting operation, deburring operation. Okay, so these are the operations can be done by abrasive water jet machining process. So it can cut any kind of material, and whatever material is cut, it has a very high edge quality. So researchers have reported that this edge quality of this cut is very high. Okay, so adaptable for remote control. So this abrasive, either you can move this abrasive water jet, this nozzle you can move on a complex path, or you can keep fix this nozzle and you can move this workpiece. Okay, so you can move this workpiece using a CNC machine, CNC control, using a CNC control. Okay, so it can be used for remote control. Okay, so any kind of complex shape can be generated from this process. And recycling of abrasives are done in case of this abrasive water jet machining, because in abrasive water jet, these abrasive particles, actually this requirement of these abrasive particles are around 5 kg per minute. Okay, so maximum 5 kg per minute. So because of this high requirement of these abrasives, okay, so these abrasive particles are actually recycled in case of abrasive water jet machining process. Okay, so this abrasive water jet machining, another example, good example is that dismantling of nuclear power plant. Suppose you want to dismantle a nuclear power plant, so you can send this abrasive water jet machining nozzle through a robotic arm, and you can do the dismantling operation. Because of this fire radiation hazard, people cannot go there for the machining operation. So you can send this nozzle through a robot. Okay, so a robot will do the cutting operation by using this abrasive water jet nozzle. So here you can see this high pressure jet is coming here. Okay, so it is coming through this orifice here, this high pressure jet, it is coming through this orifice, and at the side actually you can see this abrasive port. So these abrasive particles are coming because of the sucking action by this high velocity water jet. So it will come, and there is a mixing chamber. So this is the mixing chamber here. So in this mixing chamber, this abrasive water jet, these abrasive particles, these dry dehumidified abrasive particles, actually it will mix with the water jet here, with the dry abrasive particles will mix with this water jet in the mixing chamber. After that it will come through this nozzle, okay, and it will hit the workpiece surface here. So here actually centrally this high pressurized water jet is pushed, are delivered, and from the side actually abrasive particles are delivered. So what are the different elements of abrasive water jet machining process? Okay, so first element is the pumping system. Okay, so this first element is the pumping system, second element is the abrasive feeding system, and third element is the nozzle. Okay, so abrasive water jet nozzle and mixing chamber. Okay, and fourth element is the catcher in abrasive water jet machining process. So these are the four elements, four most important elements of abrasive water jet machining process. Okay, so now we shall discuss one by one all these elements. Now pumping system already I have told. So this pumping system, you need an intensifier to generate around 450 megapascal pressure. So 450 megapascal water pressure you have to generate, and for that actually we need a high high kilowatt motor. So generally 75 HP motors, 75 HP motor is used for generating this much of 450 megapascal pressure. Okay, so this high pressurized water jet is converted into high velocity jet inside the nozzle. Okay, so abrasive feed system. So this abrasive feeding system, this work is to deliver the dry abrasives. Okay, so to control the flow rate, control orifice diameter, and suction pressure in mixing tube should be changed. Okay, so by changing the control orifice diameter, okay, and by changing the suction pressure in the mixing tube, we can change the flow rate of these abrasive particles. So cannot supply abrasive for a long distance. So by this process where you are using a dry abrasive particles, you are supplying these dry abrasive particles through this from the side of this nozzle, and from the center you are delivering the water jet, high pressurized high velocity water jet. So by this process actually you cannot supply abrasive for a very long distance. Okay, so nowadays new system has come where instead of mixing this abrasive and water inside the mixing chamber, you can mix it this slurry, you can mix it this abrasive and water jet somewhere else, and you can flow this slurry and you can feed this over a long distance. Okay, so but in this case actually means when you are delivering this slurry over a long distance, in that case you need a high velocity, means you need a high power pump or intensifier. Okay. So water jet nozzle diameter is, so it is 0.75 to 635 microns. So this is the very small diameter is there. 165 means 0.6 millimeter. So 0.075 millimeter to 0.635 millimeter. So this is the very small diameter of water jet, means abrasive water jet nozzle is used to generate this high velocity. So even a big size abrasive particles comes into this passageway. Okay, so it will clog the entire nozzle. So that's why you have to be very much careful about the abrasive particles. So these abrasive particles should be dry enough, okay, so that it should not make any agglomeration among themselves. Also it should, the size of this abrasive particles should be maintained so that it should not clog the this nozzle. Also whatever the chips formed from the workpiece surface, it may also clog the nozzle. Okay, so types of abrasive jet nozzles. So depending on the time of work, okay, and applications, there are different types of nozzles, nozzle materials are used. So these nozzle materials, abrasive water jet nozzles, because high velocity abrasives in abrasives actually it is coming towards the outer periphery of the nozzle. Okay, so and water jet is coming at the center. So this abrasive this nozzle material, this inner surface of this nozzle, it is directly in contact with these abrasive particles. Okay, so directly in contact with these abrasive particles, that's why. So there is a huge wear out of this nozzle is there. Means because of these abrasive particles which is coming towards the surrounding or surrounding this nozzle, surrounding this nozzle. Okay, so this abrasive actually it will wear out the inner surface of this nozzle. To reduce that thing, there are different configurations of the nozzles are there. So we shall discuss all these different kinds of nozzles one by one. So there are different kind of different types of materials are used for this nozzle. Okay, like tungsten carbide, and then boron carbide and sapphire. So among these three, tungsten carbide, boron carbide and sapphire is actually most generally used. So because it has a high tool life. Okay, so this nozzle life of this nozzle is high in case of sapphire. Okay, so different kinds of abrasive water jet nozzles are generally used. So here you can see that single jet side feed nozzle. Okay, so single jet means water jet at the center it is coming water jet, but these abrasive particles are side fitted. Okay, so these abrasive particles are side fitted here. Here you can see this abrasive water, this water, high pressurized water is coming through this orifice, and it is coming here, and from this side actually you can see these abrasives, it is sucked in the mixing chamber. So this is the mixing chamber or mixing chamber here. So in this mixing chamber, this high velocity, high water jet along with these abrasive particles is mixed here in this zone, and then after that it will come outside through this nozzle. Okay, so from here to here, this is called nozzle tip distance or stand up distance. Okay, so this is called stand up distance and nozzle tip distance. So it has a huge importance of this nozzle tip distance. By changing this nozzle tip distance, you can change your material removal rate. Also you can change your this curve width and accuracy of this machine surface. So different other things also you can change by changing this nozzle tip distance. And this is the target or workpiece here. So here the abrasive water jet, whatever mixed abrasive water jet, it is coming through this nozzle here. So this is the mixing chamber here. So in this case you can see these abrasive particles, it is coming from this outside periphery of this nozzle, and water jet is coming through this inner side, inner periphery. So as these abrasive particles are coming through this outer periphery, while it is coming from this nozzle, it will do the, while it is coming through this nozzle, it will do the wear out. So it will wear out the inner surface of this nozzle, because these abrasive particles are coming from the outside periphery. Okay, so these abrasive particles are at the outer periphery. So when it is coming through this nozzle, it will wear out this nozzle. So by this method, so this single jet side feed nozzle, this this wearing action is very high. Okay, so it is simple to make rapid wear of exit part of this nozzle, and non-optimal mixing efficiency of water and abrasive. So here mixing efficiency is not good for this kind of single jet side feed nozzle. After that, there are another model which is called annular jet. Okay, annular jet and center feed nozzle. So here it is opposite. Earlier these abrasive particles are side feeded. Here these abrasive particles are at centrally feeded. And this water jet is coming from this annulus region. So high pressurized water jet is coming from this annulus region. So here better mixing of water and abrasives. So we can see here that this water jet is coming from this outer periphery, and abrasive particles are coming from the inner surface of this nozzle, and this is the mixing chamber. So here in this zone only, outside, when it is coming outside this nozzle, so there only actually this mixing occurs at the outside of the nozzle. Okay, so better mixing of water and abrasives can be observed for this kind of model of nozzle. Okay, so mixing is outside this nozzle and less accurate machining cards are wired. So here you can see there is a huge divergence of this abrasive water jet. Okay, so this curves generated is less, curves generated is high here in this case, and this accuracy of this workpiece generated here is accuracy is less accurate, means workpieces are less accurate. Okay, so third one is the multiple jet central feed nozzle. So this multiple jet nozzle, okay, so this water is coming from this at the outer periphery of this nozzle, from the outer periphery of the nozzle with multiple jet here. So you can see here two jets, there are other jets are there, and abrasive particle is fed towards the center, from the center. So these abrasive particles are fed from the center. So surrounded by multiple water jets in a converging annulus. So these abrasive jets are surrounded by multiple water jet. Okay, so it is surrounded by multiple water jets in a converging annulus. Here in this converging annulus, it is multiple water jets are coming, and abrasive particles are coming from the center here. So here in this case higher nozzle life and better mixing is there, but these kind of nozzles are costly, because it is very difficult to fabricate this kind of nozzle, because whatever this water jet is coming from the inner periphery of this nozzle, it has to be concentrated into one point. So this concentration and also abrasive particle has to be concentrated at this nozzle entry. Okay, so so that there is a proper mixing can be done here. Okay, so it is very costly because it is very difficult to concentrate all these granules from this all this water jet supply system to a certain point. So now we shall discuss different kinds of catchers. First we shall discuss why these catchers are needed actually. So when this high velocity jet is moving and it is impacting into the workpiece surface, and after machining operation, after machining what happens, whatever this just below the workpiece, whatever material is available below the workpiece or fixture available below the workpiece, okay, so it will hit that portion. Okay, so means after machining the workpiece, it will hit the bottom surface of the machine. Okay, so when this high velocity jet is impacting into the just below the workpiece surface after machining, okay, it will do the cutting operation there itself on the machine. Okay, so to reduce this unwanted machining, okay, so we have to reduce the velocity of this abrasive water jet. So how to reduce this velocity of this abrasive water jet? So in this case, your workpiece is moving here, but your tool is actually constant. Tool is actually constant. So here stationary nozzle and moving workpiece. So here workpiece is moving and your tool or nozzle is constant. And just below the nozzle there is a long pipe is there. So you can see there is a long pipe, flexible pipe is there. On this flexible pipe, this kind of construction, okay, so this kind of hard materials, construction using very hard materials are kept. Okay, so when this abrasive water jet after cutting this workpiece, okay, so it is hitting back to the workpiece surface. Okay, so it will hit the individual these plates, it will hit the individual plates which is very hard. Okay, so automatically its velocity, because it is hit by this individual blades or individual material, okay, so it will its velocity will be reduced. Okay, because of this impact motion by this nozzle, okay, on this blade. Okay, so after that this high velocity jet, its velocity will reduce and it will exit this pipe. Okay, so catcher is used to minimize the velocity of this abrasive water jet before it hits the base of this water tank, so that the tank does not get damaged. Okay, so this is the stationary nozzle and moving workpiece. So long narrow tube placed under the point of cut. Okay, so now second one is the moving nozzle and stationary workpiece. So here in this case workpiece is stationary, but your nozzle is moving. Okay, so in earlier case we kept one water tube. Okay, but in this case actually we are using a water tank. So on this, just above that water tank, we have kept the workpiece using a friction. Okay, so a water filled settling tank underneath the workpiece is kept. Transfer of the high pressure to water filled in the tank. So high pressure water jet. Okay, so after machining, okay, so it will fall on the water tank and its automatically its velocity will be reduced. So minimize abrasive water jet velocity by hitting the stationary wall filled in the tank, and to collect the remains of this abrasive water jet, flexible hose pipes. So okay, so flexible hose pipe is used when from this intensifier you have to connect this nozzle, so you have to flow the fluid from the intensifier to the nozzle. Okay, so when your pressure is more than 24 megapascal, in that case flexible hose you can use. And when your pressure okay, so your pressure is greater than 24 megapascal, so in that case rigid tubings are used to connect the rigid tubing is used to connect the nozzle with the high velocity pressure jet. Okay, so these are the different parameters. These are the different parameters which are used. Okay, so like water, what are the parameters? So water, in case of water, this water jet flow rate of this water jet is the important parameter. Then pressure of this water is the important parameter. Okay, Like what are these nozzles? Nozzle material is important because based on this material actually our life actually depends on the uh, depends on this nozzle material. And cross section of this nozzle material also important, like you can use circular cross section, you can use the square cross section, whatever you want. So you can use different kinds of nozzle cross section. And then third one is the workpiece hardness, workpiece material properties, brittle or ductile material. Okay, so these are the parameters for workpiece. Now abrasive type, what kind of abrasive type you are using, what is the size of this abrasive, and what is the flow rate of this abrasive, both are important. Abrasive feed nozzle, so this cross section of this nozzle, what is the different cross sections, what is the different materials used for this. So what are the different materials used? What are the different materials are used for this abrasive feed nozzle? Okay. Then cutting parameters, among the cutting parameters is the transverse speed. So transverse speed is one of the parameter. Stand-up distance is the one of the parameter. Cutting velocity is one of the parameter. And number of passes is also one of the parameter. Angle of cutting is the one of the parameters. So these are the different parameters for cutting parameters or machine parameters. And mixing tube, length of this mixing tube is the very important thing. So number of passes mixing tube diameter also an important parameter. So by changing all these parameters, you can change the efficiency of this abrasive water jet machine. So what are the output responses are there? Output response is penetration rate, and then material removal rate, depth of cut, curve quality, and then quality of cut. So these are the actually machining means output responses are there. So curve quality we have discussed earlier. Curve is actually when this jet is with the diameter D actually cutting. Okay, so what is the width of suppose there is a diameter of D is abrasive water jet, but after cutting you can see this is the width of cut is there. So this is called actually this one is called actually curve. So what is the curve generated is called, what is the width of cut on the workpiece surface. Then process parameters, already we have discussed water process parameters are flow rate and pressure, abrasive type, size and flow rate, water and abrasive water jet nozzle, material and design. Cutting parameters are feed rate or traverse speed, stand-up distance, workpiece material, these are the cutting parameters. Mixing tube diameter and mixing tube length is also an important parameter. So angle of cutting is also an important parameter. Traverse speed is another important parameter, and number of passes also an important parameter. Okay, so one by one all these parameters we shall discuss here. So here you can see with the increasing pressure, depth of cut actually increases. So all this depth of cut increases with increase in the pressure. Okay, so if we increase the pressure, in that case your cutting velocity also increases, this water jet velocity increases. So if your velocity increases, it heat the workpiece surface with a higher kinetic energy. So that's why you will get higher depth of cut. So now here also you can see if we increase the abrasive flow rate, so in that case also your depth of cut increases. Now here there is a critical pressure, minimum pressure or critical pressure is required to generate. So here beyond this means below this critical pressure there is no machining rate. Okay, so there is no machining below this critical pressure because a certain pressure is required to generate to gain the abrasive particle certain kinetic energy. When this kinetic energy is strong enough, then only it will do the machine. Okay, so this minimum pressure or critical pressure or kinetic energy of abrasive particles are needed to cut the material. Okay, so it is different for different workpiece materials. So this critical pressure is different for different workpiece material. So again, we can see here with increasing pressure, depth of cut also increases. Okay, so increasing abrasive flow rate also you can see. If you increase the abrasive flow rate, so in that case also this your depth of cut increases. So here another example, another graph is there. Okay, so here D1 is more than D2. Okay, so when this diameter of this abrasive jet nozzle is increased, okay, so diameter of this abrasive jet nozzle is increased, so in that case there is a decrease in depth of cut. Okay, so means for lower depth, lower diameter of this abrasive jet nozzle, your depth of cut will be more. Okay, so this critical pressure is below this pressure, no cutting action takes place. So this critical pressure is different for different workpiece material. Okay, so it depends on the workpiece properties like hardness, ductility, etc. So above a definite jet pressure, machine depth tends to stabilize. And then relationship between with the machine depth, okay, so steeper with the higher abrasive flow rate. So with the abrasive flow rate, with higher abrasive flow rate, your this machine depth also increases. So increase in pressure also means we have seen that with the increase in the pressure, your metal removal rate or depth of cut increases, but under a certain under a certain limit, or it will increase with up to some optimum level of this pressure. Okay, so beyond this critical pressure, what happens? There is a decrease in metal removal rate. So what happens? This increased pressure leads to the lower efficiency, because with the increase in pressure your velocity increases, and with this high velocity abrasive particles, it is coming outside this nozzle and it will wear out, because its velocity is higher, it will wear out to the inner surface of this nozzle. So you have to change the nozzle. Okay, so increased pressure will lead to the lower efficiency, higher nozzle wear rate, also higher cost of pump maintenance. Okay, so if you increase the pressure, so pump maintenance will be more. So now water flow rate. So water flow rate also influences the metal removal rate in case of abrasive water jet machining process. So propelling fluid enables high abrasive flow rate, okay, up to this 5 kg per minute, and abrasive velocity is 0 to, so abrasive velocity also increases up to 300 meter per second. Okay, so this water flow rate of water is proportional to this root over of the speed, pressure, fluid pressure. Also this flow rate of this abrasive is proportional to the diameter of this nozzle. So it also it is proportional to the diameter of this nozzle. So one reason is that abrasive water jet, why it is better than abrasive jet machining, because in case of this abrasive water jet machining, whatever diameter of this abrasive water jet is generated, okay, so this diameter, it is coherent. So this abrasive water jet it is coherent in nature, so it impinges or impacting into the workpiece surface into a small diameter. So it is a coherent jet is generated in case of abrasive water jet. So that's why it is more suitable for cutting operation. Okay, so machine depth also depends on the kinetic energy of the abrasive particles. Kinetic energy of the abrasive particles. So here this kinetic energy half mv square. So you can see that machine depth is proportional to this velocity of this particle square, and then mass flow rate of these abrasive particles. So above the critical value of this mass flow rate or abrasive flow rate, there is a reduced depth of this machine surface. Okay, so increase in metal removal rate, increasing metal removal rate. So we are of mixing nozzle will be there. So and then mixing efficiency will reduce. So selection of these abrasive particles will depend on the cost of abrasives, nozzle wear rate, environmental consideration, machining rate and particle strength. So now you can see this abrasive flow rate. If we increase the abrasive flow rate, you can see this depth of cut also increases. Okay, so if we take different kinds of abrasive particles for different abrasive particles, different depth of cut will observe. So among these glass beads, silica sand, granite sand and alumina, as the hardness of this aluminum is higher than all these abrasive particles, all this kind of abrasive particle, so depth of cut will be maximum for this alumina. So abrasive particle size, that is the optimal particle size is required, because when abrasive particle size is more than this optimum particle size, it will clog the inner surface of this nozzle. Okay, so because this nozzle diameter it is in the sub-micron range, if we increase the diameter of these abrasive particles, okay, it will clog the internal surface of this nozzle. So fine particles actually is used for shallow depth of cut, and coarse particles are used for high depth of cut. So different abrasive sizes for different depth of cuts are actually used. So these are actually optimized from preliminary experiments. So abrasive materials, what kind of materials of abrasive we should use? Okay, so machine depth actually depends on the type of abrasives. So what kind of abrasives we are using? Suppose if we use diamond abrasives, in that case obviously your machine depth will be more, because of this hardness of this abrasive particles is more. So here we can see this, with the increasing the abrasive flow rate, this depth of cut, so this rate you can see it is very high here. So after that it touches the optimum abrasive flow rate. Okay, so where your depth of cut is maximum, after that this depth of cut actually decreases when we increase the abrasive flow rate. Okay, so in that case, beyond the optimum value, in that case actually your depth of cut after the optimum value is achieved, this depth of cut again it is decreases, because more abrasive particles, when you are using more abrasive particles, these abrasive particles actually will collide with each other. Okay, so it may make agglomeration also. Okay, so these abrasive particles are not good for machining. Okay, so then beyond the optimum value of abrasive flow rate, your depth of cut will reduce. Okay, so here also you can say abrasive flow rate, if we increase, your depth of cut also increases. But here one interesting thing is that when your this depth of cut increases with the increasing the nozzle diameter. Okay, so here nozzle diameter is 0.25 centimeter, but here in this case nozzle diameter is 0.071 millimeter. 0.71 centimeter. Okay, so with the increase in the nozzle diameter, your depth of cut also increases. Okay, traverse rate. So traverse rate means this nozzle actually we are moving with a certain velocity. So these nozzles we are moving with a certain velocity. So based on this traverse rate of this nozzle, keeping your workpiece fixed, based on this traverse rate of this nozzle, your machining rate also increases. Machining efficiency also depends on the traverse rate of this nozzle. Okay, so traverse speed is the relative motion between the abrasive water jet with the workpiece surface. Okay, so it can be achieved by moving the abrasive water jet, or either moving the abrasive water jet or moving the workpiece. So depth of cut decreases. So this depth of cut decreases with the increasing the traverse speed. So if you increase the traverse speed, your depth of cut actually it will reduce. So overcut decreases with the increasing the traverse speed. Suppose we want to decrease the overcut, so in that case we have to move the abrasive water jet nozzle with a very higher velocity, or you have to increase the higher traverse rate to reduce the overcut on the workpiece surface. And traverse speed versus area generation rate has an optimum value. Okay, so this area generation which I will discuss, this area generation means it is the curve area generation. Kerf area generation means it can be calculated by this traverse rate, then this multiplied by the depth of cut. So this depth of cut multiplied by this traverse rate will give the your this kerf area generation. Okay. So now we can see that there is a optimum kerf area generation with a certain traverse rate. After that, actually this kerf area generated is reducing. Okay. After it achieves the optimum value, then this kerf area generated it also then reducing. So number of passes means we can use single nozzle or different passes we can use for this certain for getting certain depth of cut into the workpiece surface, certain depth of machining into the workpiece surface, or you can use multiple tandem of jet and you can move together. All these jet nozzle you can move together. Okay. So if we increase the number of passes, okay, you can see this cumulative depth of cut increases, because at the second pass, this whatever this machining cavity generated, it behaves as a means local mixing chamber. Okay. So then third time when you are using this third pass, this whatever machining cavity generated in the second pass, it acts as a mixing chamber. Okay. So that's why this number of with the increase in the number of pass, your this cumulative depth of cut also increases with the increasing the number of passes. Okay. So here you can see that, okay, single water jet with multiple passes. So here same single water jet we are using multiple pass, or multiple tandem of jets with single pass is there. Okay. So each jet makes an additional depth of penetration jet 1. So here you can see this jet 1, it is penetrated up to this H1, and then H1 max, and then jet 2 gives the H2 minus H1 as the local mixing chamber, and jet 3 gives the H3 minus H2 millimeter as the additional depth of cut. Okay. So with the increase in the depth of number of passes, you can see that with the increase in the number of passes, so we can see that we can see that your depth of indentation increases. Okay. So increase in the number of passes, cumulative depth of cut increases. Kerfs act as a local mixing chamber for this case. Okay. So this is the multiple tandem jets with single pass. Okay. So with the number of passes, we can see cumulative depth of cut also increases with the number of passes. Okay, stand-up distance also an important parameter. So with the increasing the stand-up distance, you can see your depth of cut also decreases. Okay, so higher material removal rate, higher depth of cut can be observed with a lower stand-up distance. Okay, so as the stand-up distance increases, machine depth decreases because of rebounding of the particles. Rebounding of the particles, so loss of energy give shallower depth of cut. Okay, so beyond the optimum value of this stand-up distance or nozzle tip distance, no cutting will take place, and smaller stand-up distance give deeper depth of cut. Okay, so this is the visualization of this abrasive water jet cutting operation using a moving camera. So you can see here, so whatever this jet is actually generating in case of abrasive water jet machining inside inside the workpiece surface. Now if you take a moving camera along with this abrasive water jet, you can see this kind of trajectory is actually generated in case of abrasive water jet machining process. So by tilting the workpiece or nozzle, or cutting would take place at different angles of impact. Okay. So two modes of material removal is there. One is the erasing mode at the top surface of the workpiece, and another one is the deformation mode at the bottom surface of the workpiece, where local mixing chamber is already there. So penetration rate and depth of cut is a function of time, keeping other parameters as the constant. Okay, so now from here, from this graph you can see with the machining time, you can see depth of cut also increase with the machining time. But this penetration rate actually reduces with the depth of cut. with machining time. So penetration rate reduces, but this depth of cut increases with the machining time. So process performance. So this abrasive water jet machining process mostly used for cutting purpose can cut thick material as much as 200 millimeter. This much of thick material can be cut. Okay, so curve width decreases as the workpiece hardness increases. Machine surfaces, no thermal damage, no mechanical damages are there. Machining of glass. So while doing this machining of glass by using abrasive water jet machining process, because of this divergence of this jet, instead of cutting, actually there will be a frosting operation. Applications. So any kind of material can be cut, non-metals, metals. Okay. So omnidirectional cutting. So like in wire radian process, you have to do the hole. Okay. So after that you can do the machining operation. But in abrasive water jet machining process, and from anywhere from the workpiece surface, you can start doing the experiment. So that's why it is called omnidirectional cutting. Okay. So industries like aerospace industry, nuclear industry, foundry construction, so they are using this abrasive water jet machining. Steel components, cut plates, tubes, corrugated structures. Okay, so this kind of structures can be cut. So here this is the cutting of pigeon on a granite sheet. Okay, so by using abrasive water jet machining process. So this butterfly also it is made up from granite sheet. This deer also it is made from granite sheet. It is made by a CNC abrasive water jet machining process. Okay, thank you.